Okay, hello everyone. Lance Frymire with Ocean Technology Group at UH. Been there about 5 years. I came out of Northwestern Michigan College, a Bachelor of Science in Marine Technology. My old mentor is over here, John. If you're somebody in a position to hire folks, talk to John about what you want those people to have as skills. Uh, Always awesome person to talk to over there. Uh, what am I going to talk about? EOM cables, electro, optical, mechanical cables, and UNOs. Um, Primarily 681 and the 322 fiber optic version. So the fiber optic version we got from the winch pool. That's the 322 fiber optic came from the winch pool. And the 681 is the other variety that Ella had talked about. It is the three steel light version. And I'm just going to talk a little bit about terminations, mostly related to what I've done. And if I get through this whole thing and you don't disagree with me on anything, then I've totally failed. Because this is not a best practices presentation. This is what I've found in the 5 years I've spent working with fiber in my own experiences and being a fiber optics lead for the UH ROV program. Uh, so with that said, let's get right into it. Figure out. There we go. So just starting a bunch of pictures here. On one side, you see the UH ROV on the back deck. The termination that you see on top of the tether management system here, that is a PMI Evergrip. So if anybody has seen those before, very likely they make 322 versions and 681 versions. It's a series of grips that has a little football in there, and then you slide this thing on. We have the rubber boot addition, so it needs to get wet to have its full strength as well. If it's not wet, then it's not as strong. So it has like an adhesive built into the rods. And then we've got kind of a mechanism to attach it to our TMS. And then the inside of that cable comes out and has a little cable run down into a termination box. Additionally, here is the 322 fiber optic. You might recognize some of this design right here came from the Alaska group, and we have some folks from that group here today. This is also a PMI Evergrip, and the belt comes out of the termination here and goes into this pressurized oil-filled container through a gland. And sort of the internals of that, I'll talk about a little bit here in a minute. But I also want to talk about slip rings and fiber optic slip rings in particular. This is the slip ring that we got from the winch pool, and a look at the fiber. You'll see that they come, pre-terminated most of the time, and the connectors that you get from a slip ring manufacturer are usually of the SC variety, but you can get them in ST as well. And the difference is that SC has a threaded collar with a key lock, and then ST is more of just like a spring push and twist. So if you're working with fiber optics, you want to get lots of adapters because no one piece of equipment is ever going to give you all ST. You want SC, you want LC, you want the list. It goes on, which I have a little bit later. And then I didn't have a lot of great pictures, but this is a splice as well as a copper connection here that they had done for us, which we were grateful for. But there's some soldering going on in here, but there's also a fiber that runs through the copper. And it looks like they had done a hot melt connection, is what I believe that is. And I'll talk about some of the differences in those. It's widely used by some groups, but not me. 681 to vehicle, this is for our ROV. This is an older photo that shows a long past technician doing hot melt on one side and fiber optic fusion splicing on another with splice on pigtails. But this is kind of what our termination can looks like. We've got conductors here, and we've got fibers coming out of steel lights. And you see there's a bit of a sharp bend there. And that bend is a result of the fact that steel lights are rigid. And no matter how you manipulate them in a box, they'll want to bend one way or another, introducing tension, torque, whatever, on any kind of splice that you put on the end of that. And then below that, sort of right here on the bottom side, the blue is what's called an Omicron cable. That is a high pressure fiber optic wick. So the other side of that goes to our control can for the tether management system. And it has a special connector that can go right into a control can on the outside and withstand full ocean depth. So it's how you get your fiber optic link from an oil filled container into a pressurized can without having to do a through termination or a gland. This is just yet another photo of the termination here and the sort of system that we had for Lukai at UH. And 681 going into our slip ring side. So right next to my termination box is our transformer can. And for us, because we have a 681 to TMS system that has a rotating drum, because our tether management system is not a fixed length with floats, it's actually on a capstan. And so that means we need to have yet another slip ring. And that slip ring has just another place where we have to make fiber splices and connections to deal with the fact that we're going into a slip ring yet again. So for this particular type of system, you've got a slip ring on your 681 cable drum, and we've got one subsea in our tether drum. So the splicing work in here, this is a fusion splice from steel lights going into a fiber whip that's single mode going into a splice on pigtail. These are called cheetah connectors. Generally, you can get them from multiple different manufacturers. I get ours from FIS, and that's, I think, where the trade term cheetah connector comes from, because that's what they call them. And yet again, this section here in our termination can, I have steel lights coming in, doing a loop, coming out here with a fusion splice, and I kind of use two versions of heat shrink for this because it needs to be strong enough to grab onto that steel jacketing, but also not serve as like you don't want to seal it so much that any air trapped in there gets squeezed and then crushes your fusion splice. I've seen that happen where if oil can't penetrate into that fiber sleeve, as you will, you might get a situation where the pressure at full ocean depth literally crushes some of your splice work. So you need to think about how you're protecting your fiber splices if you're going to depth, even in oil-filled containers. And I put the typical fiber sleeve that you get with a fusion splice kit, and then I put another layer of heat shrink over the steel light and kind of grabbing onto that fiber sleeve to provide a bit of rigidity there so that the fiber sleeve doesn't just wiggle its way off the end and then break the fusion splice. That's because oil is getting in there. It makes all of your fiber work and any heat shrink sleeves you put on all this stuff gets really lubricated and gets really susceptible to just sliding off whatever you're putting it on. So you have to kind of consider some of that when it's going into an oil container. So from our slip ring on the tether management system, we get to our tether and then tether to vehicle. This is the mechanical termination. As it's really fun to do, as you can see with my excellent device here to get the bolts down into what's called our chimney. To do the mechanical bit, we've got the tether that comes out, this little black boot thing here, boots up against the tether jacketing. We've got some Kevlar, and then we fill this socket with an epoxy. And for good measure, we save like 4 or 5 strands of Kevlar and just tie a bunch of knots and cinch them down into the epoxy, just to give ourselves peace of mind. And then that cures, and we trim the whole thing with a Dremel tool, and definitely never nick the green inside tether that's coming out. Never done that. Therefore, never starting over again. Then this plate gets mounted to the flush side of that piece, and then the whole thing goes in and gets bolted through these open holes here to the inside of the chimney. So when the vehicles separate, this chimney thing lowers, and it's essentially attached to the TMS through this collar mechanism here. Now looking at the ROV side of the tether, slip ring side as well, but our ROV is really small, so we don't have a lot of space. This is kind of what the termination can looks like in the ROV. And our tether internals, we've got 5 coppers, and we've got 2 K-tubes that are insulated. And in those K-tubes is 2 fibers each. We only use 2 at a time, and that has to do with the slip ring and the availability of fiber on the ROV end. So we've got 1 fiber for control of the ROV. We've got a spare or science fiber for science instruments. And I didn't get an awesome picture of this, but this is how I treat K-tube exits here. I've got a fiber sleeve. So I strip back insulation off the metal. Then I score the metal with a brand new pair of strippers. Brand new. Not rusty, not old, not dull, brand new. If you mess this up enough times, you have to literally do everything over again, because if you bend it to break, now you've got edges that are sharp bent in towards your fiber, which saw away at them over time. So you score around enough times that you almost cut through the metal with the pair of fiber strippers without cutting the fiber at the same time. You have to be really well scored such that it almost just, you can blow at it and it breaks apart. Otherwise, you have rugged edges sawing away at the fiber. And a lot of people do this with what's called a fan out kit on the other side of the metal. So it's this little device, and you stick the fiber ends through it, and there are these really long sleeves on the fan out kit. I don't believe in those because I've broken fiber at the fan out kit to K2 junction way too many times. So instead, I just use a fiber sleeve. But I cut off the sleeve from the fan out kit, and I push that over the K-tube fibers, because the K-tube fibers are really bare. They only have like a little bit of cladding on them, so they need some protection. So I take the sleeves off the fan out kit and just kind of butt them up along the fiber until I get close to the exit of the K-tube. And then I have the heat shrink sleeve, slide that over the whole works and shrink that down. And in my experience, it has not failed on me yet. And lots of people will tell you that fiber needs to be able to move inside of K2 or it will break. This seems like it would work against that theory, but so far I've had this in a slip ring junction box for 2 years and never had a problem. It must be allowing some kind of movement. It seems to work. In our actual splice termination box here, I've got some splice on pigtails that go to our Omicrons. You'll notice that they're zip tied to the adapter holder rather than in the adapter holder itself. Someone had a great idea to put this thing in there. Problem is, it is just in the wrong spot such that the Omicron comes in, takes a hard bend, and over time it was breaking the tip of our Omicron connector. And just far enough in the other direction that it was making a really sharp bend coming out of our splice on pigtail. And that sharp bend attenuates our fiber and also leads to weaknesses and kinks and more breaks. So you really have to think hard about what your fiber is doing inside of enclosed containers, what kinds of, a bend will lead to kinks and lead to breakage and attenuation. The more space you have, the easier it is. The less space you have, the harder it is. And the more you'll probably just have to experiment, whatever it is you're working. I found that loose, sort of untidy loops isn't necessarily a bad thing. The more you try to control and really restrict the movement of your fiber whips is not always the thing to do. This is the 681 slip ring coming out of our winch. And this is the junction box. It's not the stationary junction box. So for our ROV, we put like 2,700 volts through the cable. So there's 2 layers of what's called Kynar heat shrink over that copper plus electrical tape. The Kynar heat shrink is just a really high voltage rated heat shrink. And then we've got a little plastic plate going to mounting for our fiber whips coming out of the slip ring. These are SC style with ST on the other end. Okay, fiber toolkit. This is sort of my base toolkit. Fusion splicer, fiber specific wipes and pads, kind of like chem wipes, but the fiber version. The pads are kind of like a large square cloth looking thing. I get both 3-hole fiber stripping tool, precision fiber optic cleaver. I'm a firm believer in the special grade fiber optic solution and not just isopropyl alcohol for the 99%. OTDR and end face inspection tool, which is just a microscope. You can get them separate or built into OTDRs. Optical power meter and light source. Visual fault detector, which is the light pen. You want fiber bulkhead cleaners as well as the connector quick cleans like the ST quick clean pens. Fiber Q-tips, which are just like a lint-free Q-tip that you can use to clean adapters and things. Lots of heat shrink, sleeves, a heat gun, not just relying on the heat oven in a fusion splicer. Kevlar scissors, because typically if you're working with tether, it's going to have Kevlar in it. Lots of connector adapters again, ST to ST, SCs, FCs. There's lots. And canned air. And here I've got some graphics here. The ferrule types matter. They cannot be mixed and matched with great success. And, fiber cores are really small. So what I'm going to get into here in a second is about cleaning. Check the time. I'm kind of up on it, so I'm going to try to breeze through some of this. Poorly cleaved fiber is a problem. Poorly polished end faces, if you're doing hot melt, will cause problems. And it will change angles sometimes of your end face. When you change angles, you introduce air. When you introduce air, you introduce attenuation. Splice on pigtails, however, they have reflection, they as well as the splice that you're making. So with the splice on, ends, you are introducing some uncertainty with the fact that you're making a splice rather than the hot melt where you're just, cleaving the end and not actually re-splicing or re-melting two pieces of fiber together. This stuff here is just kind of taken from fiber optic communities, websites and things. Um, Fusion splices are fast, but it's expensive. Hot melts take longer, but they're cheap. It's kind of up to whoever's teaching you and your institution and the path that you want to take. But I've taken fusion splicing as my major path to victory here. End faces from the factory, though, like the splice on pigtails, I have gotten them broken out of the box. You really don't want to skip on the inspection of splice on pigtail connectors. Cleaning methods real fast. These are all the different ways that you can clean things.
You have 15 minutes.
15 minutes, okay. Cleaning schedule, it's important. You do need to clean your fusion splicers. There's optodes in there you want to clean, the V grooves that you want to clean. You want to clean the actual mirrors or what's generating the optode. You want to clean your cleavers. That's commonly missed. Sometimes you'll get a cleaver that's actually got a disc. This is like a disc razor, and you can rotate those razors so that you're not constantly cutting on the same part of that razor. So if your cleaver is dirty, you're going to have worse cuts, and the worse cut you have, you're going to have fractured, scratched, or misshapen end faces, which sometimes your fusion splicer will just outright reject. It will not splice the two things. It will say, end face shape wrong, try again. And I can tell you there's nothing more frustrating than delicately placing a steel-like fiber into your fusion splicer in the heat, under pressure, and 3 times in a row. Fiber end face wrong, and you got to do the whole thing over again. So it's really important and often overlooked to clean not just your splicing tool, your fiber end faces, but all of your tools and all of your adapters and the boxes that you put this stuff in. It needs to be clean. And your termination boxes, your slip ring boxes, those should be clean environments. The dirtier they are, every time you take something out of it, an adapter or whatever, if it's just getting rained on by dirt particles and then you're smashing it back together again, you're going to cause layered problems. And fiber strippers like that 3-hole fiber stripping tool, I know a lot of us probably have workspaces and toolboxes that live outside ships or a wet lab or something that has a door that's open to the outside, and some of our tools have a little bit of rust on them. Do not let your fiber tools get rusty. It is not the path to success. This is not copper. It does not work if they're not clean and sharp. These are images I got from my microscope built into my OTDR. And it's just to demonstrate what you can see through the cleaning methods and things I've described earlier. Most people will see those quick clean pens. They have the little spring on them. You push it twice and you think, oh, you're good to go. Well, here's what it looks like under a microscope when done on one of my launch fibers. Doesn't look that awesome, does it? It's not going to ruin your fiber, but it is important to keep in mind that those quick clean pens are not necessarily the best method if you're looking for pristine end faces. So this is like what it looks like before I did it. Quick clean pen, 2 pushes, 5 minutes later, 10 minutes later, to try and dispel the myth that if you just let it dry, it looks better. No, no, it does not. Um, and then this is that same end face when I sprayed. I did what's called the wet wipe method, which is taking my special fiber solution, spraying it on a fiber specific lid free wipe, and then dragging across like 5, 6 times. And it looks like this. Here's another look, uncleaned versus solution in the non-woven pads. Very little difference. I tend to prefer just the white version, but you can get the pads that are bigger and square in big bags. Those are fine. You can do the same method. Um, Here's another look at some other. This is a different test end. This is uncleaned with dust caps on all of these to start, taking the dust cap off. Uncleaned. Here's the quick clean pen, 2 pushes. Here's the Clee Top S only with no wet. Quick clean pen, 2 pushes, and then the Clee Top S. Some of this is going to be dependent on user, right? I can't make the argument that this is what you'll see every time you do what I did, because everybody's going to do this just a little bit differently with end faces that look a little different, have been treated differently over their lifetime, things of that nature. The Clee Top is a device that some people get the version where you click the button and there's a piece of cloth that actually moves across your end face as you hold it against it. Others, you click the button and a little sheath opens and there's a runway for you to wipe your end face across a fiber cleaning cloth. Some people swear by those instead of the quick lead pens. And this image here, I knew that this was going to happen because I took it out of a bag that has been used in oil-filled containers in the ROV. So if you don't clean your entire end face from oils and other things, you could be cleaning something, and then if you take your quick clean pen away and you rub it all over your fingers that are full of oil and sweat or whatever, or it touches anything else, you're going to get this waterfall effect where whatever you've introduced is now going to trickle right back down across your end face, impeding the path of light. Here's another look, uncleaned, quick clean pen, then the pads, and again, fiber specific solution and fiber wipes. Take home message at the end of the day, immaculate looking end faces is not going to make or break your fiber run, but it kind of could. And if you have dirt, bits and pieces attaching to your end faces, and then you smash them together in an adapter, over time, you're just smashing these things against each other. You can create pits, you can create scratches, and you can misshape the end of the end, the face of the thing itself. All this stuff, the more that gets in front of that little white dot in the center, the more problems you're going to have. And when I spent an extra hour and a half just cleaning the entire fiber run of everything in my ROV fiber budget, I got probably 5 or 6 dB savings out of it. That's usually not what's making or breaking an ROV fiber budget, but 5 or 6 is not nothing, right? Okay, quick points on core troubleshooting tools before I get into a little bit of detail on each. Optical light source and power meter are not replaced by the OTDR. They measure different things. They're used differently, and I would encourage getting both. Optical light source and power meter, a good set, $500 or cheaper. And OTDRs, about 10,000 or more, depending on which variety that you get. And especially if you're new to fiber optics, you're going to want training on how to use an OTDR to the maximum capability. If you've never worked with fiber and your boss hands you an OTDR and it says, go figure it out, you are not going to have success. I'm telling you, it's not the way to go. You need to get trained. You need to understand some of the theory so that, especially if you have an OTDR that only gives you a trace, you're going to be in a world of frustration, I promise. Whereas the optical light source and power meter are a lot simpler to use and much faster to use for a novice. Visual fault finder or locators, those are the light pens. They come built into some OTDRs, but I encourage getting your own. Going into that a little bit, use them for fault finding only after you have determined there is one. Can't tell you how many times I've turned on a light pen, saw a little bit of light coming out of somewhere and gone, oh, there's a problem, only to realize that there was no such problem and I'm chasing my tail. If you've put it onto a connector and you've got a fusion splice a foot away, I guarantee you, no matter how good of a job you've done, there's going to be a little bit of light coming out of that splice. That doesn't mean it's broken. It just means that maybe it was slightly misaligned, but it's trying to inject a lot of optical power into this thing so that you can read it on whatever the other end is, right? So you're always going to get a little bit of glow. You're going to get a little bit of glow in your connector. That doesn't mean it's broken. Use it to help. Let me blast through some of this. Optical light source power meter. It's measuring insertion loss. OTDRs are measuring reflective loss. Those are different things. Fast, simple, robust. OTDRs, they can give you visual aids with the modern ones. Use them with a launch and a tail cable if you can. It tells you the location of faults, but only in long runs that don't have lots of connectors. You can use them to record a history. You can save jobs and traces, so you can get an idea of the health over time. Talked a little bit about that, but ones that have lots of connectors, slip rings, and adapters, they've got lots of reflectivity, and those create dead zones where it won't measure. It has a hard time giving you a lot of detailed information if you've got, as some of the pictures I showed you, there's 4 or 5 different connections in the span of 20 meters. That creates a ton of reflectivity and it has a really hard time telling you the details about each of the individual legs in between those connections. Here's a trace. This is the cable that we actually just sent to onto the Thompson to go to the Hui folks in Guam. There's a little bit of a bend somewhere around 1,200 meters, but it's great at characterizing a long cable run. And here's some of the details of that. It tells you sort of where the bend is, 1,067 meters is its best guess. Sees a little bit of loss or reflectivity there. Come on. The settings for that run. So these modern OTDRs tell you a lot of information about what it's doing, and you want to use that to your advantage. Here's some short fiber whips with optical light source and power meter that get calibrated to each other. They're really good for short runs, long runs. Here's that same cable, an OTDR with a launch and a tail whip. The cable is actually this right here. You can't read it the same way that you read a long cable. And if you've never studied a trace before, this isn't going to make a lot of sense. So that's what's nice about some of these newer ones. It tells you what it's reading. And here, it's really just reading the reflection of that first connector. And this is going to say, okay, 1310, small, short width. It sees 0.04 loss, insertion loss. This is the OTDR trace of that same width. And it sees something like this one, overall loss 1.75. So it thinks there's a 1.75 loss through that tiny little width, as opposed to the last one. So the gist of those last couple of slides was to show that, OTDRs measure reflections. And when you have lots of reflective events close to each other, you're going to have a hard time getting the details of those things that cause the reflections. Where an optical power meter and light source, you can just plug it right in and it's going to tell you, okay, there's, point whatever. So they're different tools. And I really encourage getting both if you're going to dive into the fiber world. And at the ends of our fiber runs, whether it's an ROV, whether it's some device that you get from a science party that requires an oil-filled container that has maybe a single whip inside to an Omicron, well, those are still reflective events. And if those are damaged or broken, you're going to want to investigate probably first with optical light source and power meter if you're trying to eliminate short runs. Questions? Or finish things up?
Quick one. So if you have not done fiber optic connections before, or even if you have the Jason group, you're in the process of actually it now, and Ben Trad is leading that effort of the Jason group, and included in that we're doing video tutorials. So we had some internal funding. We are doing an internal fiber optic termination training session in December. The hope is that training will go really, really well. Maybe next year we can do it larger here. So